Okay. Let's get started. One sec. Can you just set? Okay, I'm putting it in software 2025. Can you guys tell me if you have access to this? Where's the tray erase? Oh, it's over there. Are you guys able to open that? Yes. Okay, cool. Okay, but first back to homogeneous coordinates. So we're not homogeneous coordinates, just the whole shebang. You have so remember we had like a pinhole. Oh God. We had a pinhole, right? And then like we have some object we're like trying to capture like a tree or something or a person. And then like through this pinhole model, like everything gets like reflected through this point, and then like you get some sort of like mirror image on the other side. Let's just say it's like over here, right? So like this part is fixed, right? This is fixed. But this is like up to the camera. I forgot to mention that last time. So like your camera could be like here, it could be like here, right? And it's like we define like the distance from the pinhole point, right, to like the camera lens as like the focal length. That's what F was, basically. And it's like, um, and then this is obviously the depth. This is the coordinate here, it's the depth, right? And so like, um, let's say like this is like x prime and y prime, this point here. And like its corresponding spot would be, I guess this thing over here, x comma y. Like, does anybody want to like tell me the relationship between x and y? It's just like geometry or triangles, right? So like, yeah. Any ideas? It's helpful to think about this like looking like this way. So like x y would be like looking this way would be this by x and I guess up or down by y, right? And how does that map to like this side? Which is when you're looking this way and I'm trying to figure out like directions. Any ideas? So like it's a triangle, right? So let's say we're looking at x, so like we're looking at like this plane essentially, right? So I'm assuming that the x direction when looking this way is like this way and y is up and down, right? So if we just isolate x, like we know that it's forward by z and like to the left or right by x, right? So we have a triangle, right? When looking this way, we're backward by f now. So how much are we this way by? And we know that since it's like through a pinhole point and these are all straight lines, like these two triangles are similar. So essentially what I'm saying is that this triangle is similar to this triangle, and this is x prime, right? So like what, well, how do you express, let's say, how do you express x prime in terms of x? Yep. Yeah, nice. So x prime is equal to this, right? And then you can do the same thing with y. So this is kind of like the main thing that I think whenever people says, or I didn't explain well, rather, last time. So with this in mind, right? Uh, like there's some like other stuff. So someone like go and like give me like the units of this. So like with X and Z are in like inches or something in the world, let's say, or centimeters, right? What is it? What is a unit of F? Not. Oh yeah, pixel. Yeah, that's right. Because these are in like inches or centimeters. Z is also in inches or centimeters, right? And then what is this? This is in pixels, right? So F needs to be like in pixels, right? So like, does this work when like your camera isn't a square anymore? Like when your camera is like, let's say, you know, 1080p by I forget what the other dimension is. I don't know. But like let's say it's not square anymore. Like would this still apply? I mean just intuitively, like what are we doing here? We're multiplying both x and y by the same ratio, right? F over z. So like if this image isn't even a square, does that even like work anymore? Mm,
You instead of you won't you have the exact same image. Like everything in the original square image, if it were square, is now mapped to the rectangle. So it's not just like you cut off the top one.
Yeah, it's just like it won't be correct. So like basically like if this is wider than this, then correspondingly, like this essentially it's stretched out, right? So this will be bigger. So like people usually introduce like another constant called K and L. I can't even use this marker, I don't know. K and L to like really map this across. And like, as I said before, there's some like centering issues where you want to like basically propose some point as like the origin, right? So then you also have like a plus CX and plus CY. Everybody remember that, right? So that's our final equation. And what people usually do is that they abstract away fx, right? They abstract away fx and they replace it with something called alpha or fk, sorry, and they replace FL with something called beta. Yeah. And then going to what I was saying before about homogeneous coordinates, these are equations. We have so as you change coordinate systems, like this for mapping from 2D to 3D, like remember how I said that any like point along the way would like be a valid like sort of projection, right? And so that's why what people usually do is that like they add like an extra coordinate to x, y, x prime and y prime, like with the z, and that's one. And that's kind of to note, kind of to denote that like this thing could be like any point along like this sort of thing. That makes sense. Like I just multiply this by a constant, like a, right? And then like it will be mapped like further down or something. But like it's just like show that it's the idea that like all these points are like actually equivalent. Like the same set of x prime and y prime could like, describe a bunch of possible like maps, right? And then since we're adding like one dimension to like the image space, we also need to add like one more dimension to like the world space. And these are called homogeneous coordinates, by the way, when you like add like an extra coordinate or extra dimension to everything. And then like to gloss over the details, like this, we did this last time, kind of. I derived this for like the 2D version, but it's like kind of the more standard 3D version. You basically have like alpha and beta here, and one, and you have CX and CY. And they just confirm that like when you multiply these things out, like you get this. Oh shoot, I got wait,
You're missing a RT.
yeah, I'm missing one more. A bunch of zeros. Yeah. Oh, because now you have 4 here.
It's just to make it so you can actually multiply.
So like this is like 3 by 4 and this is 4 by 1. So it turns into 3 by 1. Yeah. And the main reason for this being all zeros is what this maps to like this last coordinate, which is irrelevant to us. Right. Okay, cool. And then again, like skipping over like what I already covered last time. People usually like at least for this section before we introduce rotational and translational like matrices, they just abstract this into like this. And further abstraction, and they call this K, which is what we talked about last time, K matrix. Okay. Blah blah blah. Skewness and distortion, we covered that. And then it turns out, so like, let's see. Okay. So it turns out that like these are for the cases when there's no rotation, no translation, and this maps to R, this maps to T, right? It's kind of the base case. There's no translation going on. No rotation is just an identity matrix, so no rotation at all, or either, right? So when you want to account for those two things, this equation becomes RT times world coordinates. So that's like where we got to, like last time, basically. Does that make sense? Okay, hopefully like this is like a little more clear now. Okay, on to like stuff to cover today. Oh shoot. Okay. So okay, I'm just gonna do this. All right, so we're gonna cover 5 things or 4 things. I didn't have time to do the first slides, PyTorch basics, so we're gonna do that next week. But yeah, everything else. Onto image segmentation. Okay, so if you recall from last time, we talked about what? We talked about key point detection. We talked about stereo vision. These are all like for the purposes of like extracting useful features out of data to like train downstream tasks on them, right? So another thing that we might want to do now, a downstream task that we might want to do is segmentation, right? Like give it an image, how do we like section away like useful things? And I think like a really like cool example of this that's come out like relatively recently, is called like SAM or segment anything model that I think Facebook came out with. There's like really impressive results to be honest. Oh, I guess we'll try a demo. Or I'm not gonna try a demo because there are cookies. But I can't see it because of the full screen widget in the way. Oh, I got it. Yeah, I agree. So yeah, it's like really cool stuff. So, like given any image, like it'll like let's say this one, right? This is the first one. Okay, yeah. And we select anything, I guess, and it'll like segment it out like almost like exactly. So it's a bad example. But you get my idea, right? I think in the paper itself, they had like a lot of cool pictures that I remember. Um yeah, stuff like this, right? It's able to like segment, I guess almost everything. So this is what segmentation is, right? And then like before like we had these big foundation models that was trained. I think this was trained on what? 10 million images or maybe something. Oh yeah, here. 11 million images with 1.1 billion high quality like masks. So like segmentations. So like that's a huge amount of data, right? So like before we had all this compute and all this data to like make these nice foundation models, we had to like resort to more classical segmentation techniques, I guess. So like one of them is why is this? So like one of these is like as we said before, thresholding, right? You just threshold with the histogram of intensity, you get some sort of segmentation going on, right? That's very basic. Um, Another technique called watershed algorithm. So like basically you take an image and you kind of map its usually intensity values to like the height coordinate. So like you see over here we have an image and we basically map for each pixel like its intensity as a height. And then what you do is that you kind of if you imagine like pouring water on the whole thing, right? Everything's gonna like water's gonna slowly come up. And whenever like kind of water in like two regions kind of meet, that's considered as like an edge to like segment on. Right. So I guess to show this like um let's say that like looking at it from like a this point of view, right? We have like maybe like this is our topological map and like it goes up further up here. We like start adding water like here, and then here and here, right? And then at this point exactly like these two things like meet. So we consider this as an edge to segment off. And it's called a watershed algorithm because I don't know, it's like watershedding. Okay. And then K-means clustering is it's basically when you take each intensity of each pixel and you just cluster them. And like what this essentially does is that like you just group colors or group pixels by color. You guys know what K-means is, right? It's like just some like clustering algorithm that given like a bunch of like vectors will like group them into like clusters. Yeah. And nowadays like with the foundation models like Dino, like I mentioned last time, you can also it turns out that running clustering on the vectors that Dino gives you like is quite effective. Like you can basically do this um without much extra work, like some minimal fine tuning. Okay. Next up is ML machine learning approaches. So I guess the first, you guys know what a neural network is, right?
Mm.
You guys know what backprop is? And kind of, all right, I'll look back to like PyTorch basics, or I'll like talk on the board because we need that for PyTorch later. But anyway, so UNet, right? So like the main idea is that um you have you want to capture both local and global segmentation patterns, or like it doesn't have to be restricted segmentation. Like for this like this unit architecture actually applies for a lot of other things. For image classification, it also applies. Like if you guys heard of ResNet, this is kind of like what it looks like. But basically the idea is that like you want to basically look at the picture from all like points of view, I guess, like from like a high level point of view and like a really local like detail point of view. So if someone can like guess like would the first layer on the like farthest left side, would that be like a very granular structure or like a very like high level structure? And like in contrast, what would the last bottom layer be? As you like, oh, I guess I didn't explain like the diagram. So like, you guys know what like convolutions are, right? At this point, right? Like given like a big image, you can like given a kernel of size more than one, you can like shrink it down, right? So we're just basically successfully applying convolutions. This thing called max pooling, which is basically when you apply a convolution and you just take the max of like a group of things, and then batch them. Oh, they didn't do batch them. But yeah, but just think about it as basically applying a bunch of convolutions and like going all the way down and like up reversing the convolution, like increasing the image dimension all the way up. And then like what these arrows across skip connections, which is basically like you want the reason you have skip connections because like as you upsample, actually that'll give it away. I'll explain what skip connections are after you guys answer the question. So like which the top does a what like sort of dimension or like what kind of overview is like the top one versus like the bottom like last block. Like what's local and what's like overall. Yeah. Right. Oh wait, hold on. No, overall it's not the top. Wait, does anyone want to tell me why? I guess it's helpful to think about in the reverse, right? You're applying a bunch of convolutions from like to the input image, right? So um with each convolution, you're aggregating like local data and then combining it, right? So as you play more and more, like at the end of the day, you're just gonna get like what? I think it says over there, or it doesn't say. But you're gonna get like maybe like a 16 by 16 image from like a 1080p image. Like at like when you get all the way down to it, that's like basically like a high level overview of like the entire model or the entire image, sorry. But like initially it's gonna be still relatively like fine grade, right? So that's that. And the reason you want skip connections is because as you like upsample again, as you like apply convolutions downwards and you like inverse the convolutions, right? You want to like give some guidance like to the model as like what was learned before. So you just directly feed the output of like the corresponding like level from like the downsampling step to the upsampling step, basically. You kind of like help the model in a sense. It's like training wheels. Does that make sense? Right? Because like imagine like if I gave you like a really blurry like picture and I asked you to like recreate the original image, that's like really hard to do, like at least if you're not a diffusion model, right? So like so as a hint, I give you as input of the output of the same size from like a different side. And then maybe you can like more easily construct like the image. So that's what skip connections are. Fully convolutional networks, just like a fully connected network, which I'll maybe explain later, except you just have convolutions all around. And other approaches, YOLO, you only look once. That's like a pretty famous one because it's lightweight and it like does inference really fast. So it's basically like another model that like well, given an image, like output a bunch of masks. We might have you guys implement this. We'll see. It's actually not that bad. And then SAM is like what I just talked about. And I think that's it for image segmentation. But going back to PyTorch basics, like I think most of you guys have probably heard about PyTorch at this point. Maybe until like 2 years ago, like there was a huge battle between like TensorFlow and PyTorch to see what like when I guess like who would become more popular. And like at this point, PyTorch I think has become like the de facto standard. But the reason it's so like awesome or not awesome, so like popular is because it like like there's this thing called AutoGrad in it that makes your life really easy as like a machine learning practitioner. Um, and so like as a quick recap of last week, remember that we had models, right? And like a huge thing in the models was like what gradient descent, where you like take a derivative to like see what direction to nudge your ways into, right? And so what AutoGrad and PyTorch does is that it like in the past before PyTorch, like given like any arbitrary model, you had to like calculate the derivatives by hand, right? Like you had to like manually like see, okay, if I pass in an input like this layer will do this with these weights, blah blah blah, and I'm gonna apply the derivatives by hand and like basically like write out the loss function like manually, right? And like the gradient updates manually. But with PyTorch and AutoGrad, all I had to do is like just specify the forward function, which is basically like what do I want the model to look like, and it'll handle everything else for you. It'll like do gradient descent, AutoGrad, all that for you. So if you read papers back in the day, like maybe or at least in the appendix, there'll be like 2-3 pages of like just math, just like doing these derivatives and everything because like AutoGrad wasn't there, like people had to do this by hand. But with PyTorch, like it's automatic. And the main way this works, is basically by storing activation values at each node, which is helpful for backprop. So I guess taking a step back, I think hopefully everybody knows what like a neural network is. Like basically, oh god. You have like again, like thinking about our model, we have like some input, right? Let's say it's three-dimensional, right? It goes through a bunch of like layers. So like layers are like each of these things, right? And like it's called a fully connected layer if like each node here takes as input everything else from the previous layer. So it's fully connected. So you have a bunch of these layers, you do blah blah, and then like at the end you like pull it together again through some layers or through some connections to like some output. And like all of these layers are usually some affine transformation with like a non-linearity applied on top. So like maybe like the output of this would be the sigmoid function applied to like, let's say this is x, y, and z applied to like weight 1 x plus weight 2 y plus weight 3 z. Right, this is what the output of that would be. Does somebody know like why this non-linearity is like so important? Like basically like without this thing, like this whole thing would not work at all. It won't learn anything. Okay, well, wait, how many people here have taken like 240 or linear algebra? Okay, well, okay, so basically the thing that you learn, there's a like linear, so like basically you guys would agree that this is like a linear transformation, at least like even intuitively, right? Like these are, you're mapping a set of points in like a straight line because you're just taking like a mixture of them, right? It's like completely linear, right? And it's like there's a big thing that you can prove where basically the linear, when you apply linear transformation on input and then apply another linear transformation on that input over and over again, you can represent that entire thing, which is our entire model, by a single linear transformation. So like basically what I'm saying is that this is no more powerful than just a single layer, than just a simple multi-layer perceptron, or single perceptron, sorry. And as you learn in maybe 520 or something, like a perceptron is like not that great because like if you have an input space like XOR, for example, where like let's say you're trying to like classify this, like there's no way a line can like do this, right? It's just impossible. You can't draw a line that like somehow like does this right. So the reason you add nonlinearity now is that you can like maybe map more expressive functions in a sense. And provably like this is able to map any function in a universe. It's like some theorem out there. Um so yeah. So now what is backprop, right? So remember how I said last time, like you have a loss function. So like after the output, let's say this is O, you like have a loss function L of O that gives you like some value, right? And then gradient descent is like you take the derivative, you take partial L with respect to like whatever weight, and then you like, this is the gradient, right? So like I would take L with respect to L1, and then I update like weight 1 here with like whatever this value is, right? So the big problem is like when you have this huge, insanely complicated model, how the heck do you find how the final losses relate to this, right? And like it's not a stupid way, but like a general way could be, you could be like, okay, let's see like you can, everybody can see how you can like express the loss as a function of like this weight 1, right? You just have to like feed in an input here and then like see how like, so this would be like sigma of W1 X, and like the other terms don't matter because we're just worried about weight 1 right now, and you just pass it through again, and you pass it through again, and then at the end you get O will be like some function of W1, and then you take the derivative, right? And you have to do this for every single step. And like so like at this point you gotta do all the same computations. With W2, you have to do essentially all this like the same sort of passes again over and over again, which is like really inefficient. So all backprop says is that if you, it realizes that like after this point, like the computations that you do like with this one and this one are the same, right? So like what if you just cache like the gradients and like, and yeah, that's it, right? And then if you have the gradients here, then you can just calculate the stuff here in one step. So the idea with backprop is that you just start with the last layer, you calculate the derivatives with respect to like O and L, which should be readily available because like it's just whatever the values are here. Let's say O is equal to like the output of this A, B, and C. They know O is equal to A plus B plus C, and then you can like really easily calculate the gradients, right? And you just update that, and they know for a fact that the stuff here is just a function of this, right? And that's mainly due to the chain rule, which I was kind of implying, but like um the loss with respect to some arbitrary thing here, like Z, for example, is equal to the loss with respect to A times the loss with respect to z, right? So like if I cache this value here, if I cache partial L partial A, which I did in the prior step, then I could just get this within one step. So like that's what backprop is. You just cache the values, you go to the next layer, you use what you already computed, you calculate values in this layer, and you go to the next layer. That's what backprop is. And so what PyTorch does automatically for you is that when you create a model, like at each node, I guess, like and you like implement a forward pass where you when you send it like it's when you think about it, right? When you send the inputs in like this way, like you can like you can cache like the values of the activations and like with some hand waving like it'll able to like do this like differentiation thing for you. I'll have like better explanations like next week as like when I have like a notebook and stuff for that, but like that's like the high level overview. So yeah. Okay, on to the next one. Optical flow. So I talked about this last time, but optical flow is like about trying to find like the change in the rotation and translation matrices across time, right? If your camera is moving, like how does R and T change, right? Um, so okay, yeah, uses in robotics. I think I have to cover this. So like you can estimate motion, like from that, and that could help you stabilize a drone. And there are two main types of optical flow. There's sparse optical flow and dense optical flow, and it's a trade-off between like information and like complexity, right? So like sparse optical flow is like when you take key points that you calculated from some prior algorithm, like SIFT or Freak or whatever you mentioned last week, and then you just do optical flow on those points. And the idea is that key points are representative of an image. So why, if you're just trying to like estimate like the optical flow of the entire image, there's no point in doing everything, right? Just like do the specific points. Dense optical flow is like for other applications where you do want that pixel by pixel like value for optical flow. And yeah, and like obviously like you get more expressiveness and more power, but it takes more time to calculate. So like into like little derivations. Um, so the first line is called a brightness constraint. Or actually, before I like go into that, let me explain what the variables are. So I is intensity. So I have x, y, t is basically the intensity at location x, y at time t. Yeah. And so the idea is that you have this brightness constraint where let's say something moves, right? So it's gonna be initially it's x, y, t, but like after like delta t time steps and after a change in x and a change in y, like if they're the same pixel, their brightness or intensity should still be the same, right? Because they're the same thing, right? So that's where we get the first line from. Like everybody gets that, right? Okay. And then, well, what is the right hand side, right? You can take the first order, or maybe it's the second order. You can take some Taylor series approximation, right? Because the idea is that delta x, delta y, delta t are like really small. Like if you have a video input, like the small movements are like hopefully you have enough frames where like you can say that the deltas are really small. And so therefore all you have to do is just take the first order approximations with the Taylor series. So we just say we approximate the right-hand side by the initial points plus just the first derivatives, right? In theory, like to make this actually exact, you have to take the second order derivatives plus the third order. But we just say, hey, like those are so small anyway, let's just throw those out. Right? And we can make that assumption because delta x is really small. Because like remember the next term would be what? Some derivative times delta x squared and then plus delta y squared and then it'll be cubed. So like those will get really small. So the idea is that like if those are small enough, then we can ignore them. Basically, right? So then you get the second line. And if that's true, that means that like the deltas things, they must add to zero, right? Because of our brightness constraint, right? Everybody with me so far? Okay. Huh? Why did they add to zero? Yeah, so like the first equation tells you that I have x, y, t to go to that. I have to go to, yeah, so because I use the first order Taylor series approximation. Okay. Okay. Like just to touch base, like to like contextualize everything, right? What does partial I partial x mean? Okay, so like the derivative of I with respect to x. Okay, that's what the equation means, but like conceptually, what does it mean? Yeah, so like at your particular point x, how does like the intensity change in the x direction, right? And partial I partial y is similarly at your particular point, how does the intensity change in the y direction? And partial I partial t is like at your particular at this particular time step, how does the intensity change? So And delta x is just a literal change in x. So that's not so useful for us, right? Because like, what do we want? We want the change in what with respect to what at the end of the day. We're trying to estimate, I guess in this case, I guess the equations give it away, right? We were trying to estimate the velocity of like the x direction and y direction, like how fast x is moving with respect to what, and how fast y is moving with respect to what. Yeah, time, exactly. So we want partial x with respect to partial t, right? We want to see how fast x and y are changing with respect to time, right? So we want, oh God. With partial x with respect to partial t and partial y with respect to partial t, right? Like, does somebody want to take a stab at like converting from that third line to like somehow getting what we want? Okay. You just need to do one thing. It's a one line. So go on. Sure, where v of x is equal to like, well, if I tell you what things are equal to, then it'll be obvious. Yeah, that's right. So yeah, Brennan recognized that. Oh, he's the electrical team lead, by the way. But anyway, so you, yeah, so you just, I'll do the reverse way to like for clarity, but you just, what do we have? We have. So the first thing we do is that we divide everything by delta t, because what we want at the end of the day is like delta x with respect to delta t, right? So when we just divide it to get what we want, so we get right here. Right, what we get. And so this is what we want, right? Just the change in x like with respect to the change in t, right? As these things approach zero, you get this is what we want. That was the assumption. Like, so this we were going to call I of x. This is what we're going to call v of x. So this is the optical flow equation, right? Everybody, okay. And just like kind of non-intuitive, right? Well, actually, before I explain that, like everybody knows what each of these things are, right? So like, this is like the change in intensity with respect to x, blah blah. This is our movement, right? That we want to, or yeah, and then this is like kind of the change in intensity, like from time frame from frame to frame, right? That's what those are our type stuff. So, what are our unknowns? Like given two frames, right? What do we know and what are we trying to find? Like what can we calculate immediately given two frames? The eyes. Yeah, exactly. So like you just literally take in between two frames at this particular x point, what is the change in intensity? Right? And then what is the change in intensity in the y direction? And then so like this would be like the difference across frames. And this would be like locally in this one frame, like what the change in x is in intensity. And this will be locally in one frame. But yeah, we'll go on. Yeah, so that I was getting to that bit, right? So basically, like if you just consider one pixel, like you would have one equation and two unknowns. So we can't derive v of x and v of y. But if we have multiple points, right? We can have a bunch of these equations and we can approximate v of x and v of y. So yeah, there are two unknowns. So like usually you need to have more than one point to like map up. So that's why with key points you like I'll go to the next algorithm. Put that in mind. So Lucas Cannon, basically an extension of this idea. Very simple. Does someone want to guess? Like, so like, let's say we want to select feature points. What would we use to select feature points or key points? Yeah, sure. We can use, which is what? Do you remember what it's called? I think it's called brief or something. Or you can use sift, right? Select feature points. And then we just apply the equation from last slide. And you approximate v of x, v of y. And if you're worried about noisy data or whatever, you just apply RANSAC, which I also talked about last time, right? So this is how this is how all this works. So they call this the Lucas Cannon method because this guy put it together, I guess. Cool. So like this is how you do optical flow. And this is this sparse or dense optical flow? It's sparse, right? Because we're just using key points. Okay. Um, Thornbeck's method is for dense optical flow, and it's a little more involved because you're not just using key points anymore. Also, like before I go into that, like any drawbacks of Lucas-Canal method?
Yes, like.
Yeah. So like let's say what if like the thing moves insanely, like moves by a lot, right? It's not gonna because the assumption again is that the changes are kind of minimal. Okay. Any other drawbacks? Oh, and the reason that we have to limit ourselves to that is because we already told ourselves we're going to use key points, and therefore that's a limited number of points, and we don't have access to the entire frame, right? And so therefore we can't do anything about like large changes, right? If we had all the pixels, maybe we can try to like map things across, but we can't. What's another drawback? Like backgrounds, right? Like let's say like you're videotaping like this whiteboard, and you move everything, like it's everything's still gonna be white, basically, right? So like it's not gonna do well because like visually there's not that much of a difference. Although I guess that's a problem with like flow algorithms in general, there's not much you can do about that. But anyway, Farnback's method, which is a dense optical flow algorithm, will like solve the problem, kind of solve the problem that Monica mentioned. Um, what it does is that it considers each pixel, right? Because it's a dense algorithm now. At each pixel, you try to approximate like the intensity by like some polynomial, right? So imagine at each point you take its neighboring set of pixels, let's say like a 9 by 9 square or something, then you have like some sort of curve, right? You try to fit a polynomial onto that, okay? And then that's for one image and one frame. And then for the next frame, at that same point, you try to fit another polynomial. So now you have two polynomials, right? And then what it does is that it sees what does it change in x. So sorry, we don't need this anymore, right? Okay. So like, let's say in frame one, at like x, y, it fit this polynomial. It's called like P1 of x, y, right? At frame two, it fit P of 2 of x, y. And so the goal, what is the goal? Does someone want to tell me? Like, kind of guess. We're trying to, it's like, we're basically trying to find like what transformation in x, y direction can we do to like basically map P of 1 to P of 2, right? Does that make sense? Like P of 1, like at frame one, you have this polynomial. At frame two, it becomes like some different polynomial. So like, how should we, the question is, how much should we shift P of 1 by to like get it to match to P of 2, right? So like, how does that look mathematically? Hmm? I mean, it could be a skill, but like how, yeah. Yeah. So like, you basically want to find P of 1 x delta x, P of y delta y, y plus delta y, such that it's kind of equal to P of 2 x, y, right? And like these two things are kind of the optical flow, right? Okay, cool. So that's the first step, right? So the answer is on the screen. Compute the displacement for each pixel. And like you can like solve this since this is a polynomial, this is another polynomial. You can approximate this using least squares. If you take a stats class, you probably learned this. Okay. Now, the problem of flows at different sizes, right? What it does is that it uses a thing called Gaussian pyramids, where basically it just increasingly applies Gaussians onto an image, increasingly blurs it, and then applies the same optical flow algorithm. And the idea is that like after like I don't know 10 Gaussians, like global changes will be like kind of approximated like closely, right? So what this is like where have we seen this idea before? First today, and like secondly like from like last week. We've seen this idea once already today, where we apply a bunch of Gaussians a lot to like manage like different scales. Or not Gaussians literally, but like we applied this thing a lot to like manage things at different scales. It was like the second thing I talked about today. The second slide I talked about today. Yeah, the unit, right? We apply convolutions. It's the same idea. Um, yeah, and like more generally, people call them as feature pyramids. If you take 680, like they'll talk about that. But yeah, you use and then like from last week, like where do we see this? You guys, I don't expect you guys to remember. So like we use it in Sith, right? With the difference of Gaussians. Remember that? Yeah. So like a lot of these things have like the same motivating ideas. Um, but yeah, so now you have flows across the entire image. You so like the kind of novel thing about his method is that like most people, or you could call it a day, right? You can be like, all right, for each pixel, I have now some flow. And I'm gonna output this. But like he takes it a step further by like applying the flows to the image to get a new image and then repeating the algorithm again. His idea is that like there's no shot that like this least squares regression problem will like exactly get this the first time around. Right. So he applies the flows to an original image, gets a new image, and then applies optical flow between that new image and like the second frame again and again and again. And then you get a bunch of delta x's which you add up at the end. Right. That makes sense to everybody, right? Okay. Um, and that's it. And then now Alan's gonna talk about SLAM and some other things.
Yeah.
Yeah.
Okay, cool. So the next thing we have is SLAM. So SLAM is simultaneous localization and mapping. So this is going to be, I guess, like specifically useful in the context of the IARC problem. So we're trying to create, we're basically, we have a robot that's moving through the environment. We want to create a map of the environment that's very accurate, as well as create kind of a trajectory for where our robot is moving in that environment. So for SLAM, how do, is it not just clicking on this? Oh, it's not in the presentation. Yeah, you're right. Okay. Sorry. Okay. So the basic definition is how can we create an accurate map of our surroundings and localize ourselves in that environment. So for SLAM, there's generally like a bunch of different types of SLAM you can do depending on what sensors you have. So you can do it with camera data, with motion sensors, and very, very commonly, especially you'll see in like EV cars, just like not Tesla, basically any other EV car, they use LiDAR for their SLAM. But for a lot of the stuff that we'll be doing is going to be monocular camera. And basically that just means like we're going to try and do SLAM with just one camera. Doesn't even have to have a depth camera, mostly just like an RGB camera. And we want to output the map of the environment plus the path of the agent in there. And the problem with SLAM is that you kind of have this chicken or the egg problem. Like, should we first localize it? Like, how can we, in order to localize ourselves, we need to know the environment, but in order to know the environment accurately, we need to localize ourselves. So that's kind of a problem here that we're going to have to address. And there's going to be many things that you'll see that are kind of repeated, specifically for the type of SLAM we'll be doing, which is called orb SLAM, but I'll get into that later. So generally speaking, for SLAM, you can imagine you're this triangle robot and you detect like some features. So the first thing you're obviously going to want to do is feature detection. So you detect these features and then you move. And a lot of times for SLAM, you'll have an IMU, which gives you kind of an estimate for how much you move. So we can first get that estimate of where we are now based off the IMU, based off what the IMU reading tells us. And then once you move, you do another feature detection. And then based off where you are relative to those features, you can actually update your location so that way it best matches. So the IMU is basically like a guess, and then you do feature like mapping, so that way you get an even better idea of where you are. That's a basic idea of SLAM. And so this is kind of just a workflow for if you're doing, I guess this is using LiDAR. You basically want to extract landmarks, associate the landmarks to previous landmarks that you identified. And then EKF here is extended Kalman filters, which I don't think applies to orb SLAM, so I'm not going to go too much into detail on that. But that's a general process of how we do this. So for monocular visual SLAM, we're going to use something called orb SLAM. So this is oriented fast and rotated brief, and I'll go into more about what fast and brief are. But for the general workflow for this is we're going to use a couple frames to first initialize our map, and then we'll do tracking and local mapping. So tracking local mapping is kind of like it's like a repeated process where we track where we are, and then we create a map based off that, and we match it to our old map. And then another important part about orb SLAM and all SLAM in general is that you have to do loop closure. So if I end up in the same spot, I want to make sure that I think that I'm in the same spot. So this is a problem that you'll have a lot, especially with things like SLAM. If you have like a longer period of time in which you're moving, like if you have a small error in between every single frame, then if I have like thousands of frames stacked on top of each other, then I end up with a very big error, and I'm not anywhere close to where I should be. So the first thing that we'll do is key point detection. So specifically for orb SLAM, we use FAST, which is features from accelerated segment test. And this is this is really fast. You basically pick out corners by checking the intensities in a circle around the pixel. So you can see, I'm just looking at the intensities. And if it's a corner, then you should expect that like in most directions, it should be pretty different from that pixel. Because you'll have different intensity changes in like probably at least like 3/4 of that area. So yeah, so it just very quickly does this mapping of circles of intensity around each point to pick out corners. Obviously, this is it's very fast, but it's not great at picking out good features. So we can refine this using a Harris corner score. So basically, what this does is for each corner, you want to find the gradients of the intensity in the X and Y directions. And then you can actually create this matrix. W there is basically just a weighting factor, which weights points closer to each feature higher than points farther away. So it's like a Gaussian. You can imagine like the center pixel where you're considering or the feature that you're considering has a higher weight, and then as you go further, it gets a smaller weight. And then you just want to create this gradient matrix. And then in order to solve this matrix, I don't know how much you guys know about linear algebra, but the eigenvalues of this 2x2 matrix are basically going to tell you like how much you change in those directions. Like the eigenvalue gives you an approximation for how much your intensity changes in those directions. But actually calculating eigenvalues kind of takes a while. So in order to do this, we can actually estimate the eigenvalues by doing this by calculating R. So R here is the determinant of the matrix minus K times the trace of the matrix squared. So for any matrix, you have, so obviously you guys know what the determinant of a matrix is. The determinant of the matrix is always equal to the product of the eigenvalues. And then the trace of the matrix is always equal to the sum of the eigenvalues. So I mean, in this case, we have a 2x2 matrix. So what we have is the determinant of M is just lambda1 times lambda2. And then we have trace of M is equal to lambda1 plus lambda2. And then, so you can see here, when you're multiplying numbers together, if they're both big, you'll have a very big determinant of M. And you'll have a decently sized trace of M, but the product should be much larger than the sum, in which case R is some big number. If you have one big and one large, then your determinant will be not as big. It'll be like limited by the smaller one. And then the trace will also be like, the trace will be limited by the bigger one. I don't know. Have you guys learned this? Okay, cool. So, okay, so in that case, you get R. Basically, if both eigenvalues are large, R will be bigger. If both are small, it'll be smaller. And what you can use this for is you can imagine if we have one big eigenvalue and if we have both big eigenvalues, it's likely a corner because that means when we go in the X direction and when we go in the Y direction, there's a big intensity change. If we have one big eigenvalue and one small eigenvalue, that usually means we're probably along some sort of edge. So if you can imagine if we move against the edge, then we have a big intensity change. So that's a big eigenvalue. But if we're moving along the edge, then we'll have a small eigenvalue change. And then obviously, if both eigenvalues are small, that probably just means we're like on a face, like just some flat object. And then so that means we can filter out our features by calculating this Harris corner score. The next thing we do is we actually try to we want to use brief. So I'll get into that later. But in order to use brief, we want our features to be orientation invariant. So like if I have a corner here and I'm looking at it from like this direction versus if I'm looking at it from this direction, right? The intensities around it could be slightly different. Or sorry, like the way I'm looking at it, my orientation to that point could be slightly different. So in order to eliminate that, we want to get an orientation invariance. Is we assume that like if I'm looking at the point, the intensity of the points around that point should be relatively the same with respect to that point. So for each point, we calculate the gradient of the largest intensity, and then we call that the direction of that feature. So that way, like if like I have from this angle, I have something here, and then I have the strongest gradient over here. Then if I look at it from like this side, this part with respect to this gradient will still be stronger in intensity. So that means the gradient will point here. If I'm looking at it from that side this way, then if these pixels are still stronger, like stronger intensity compared to like over here, for example, then it'll still point the same way. So no matter which way I look at it, the relative intensity of the pixel should be the same. So the gradient should be the same, in which case we get a rotation invariant vector. And then after that, we can apply brief. So this is binary, robust, independent elementary features. So basically what we do for brief is for the features that we have at this point, we just kind of take a patch around it. You can just think about it as like a circle around it. And then we get the orientation vector, and then we align the orientation vector. So no matter which way we look at it, it's facing the same direction. And then from there, what we do is like, I guess like at the very beginning, we initialize a random set. We initialize the size of the patch, and we also initialize a set of like point correspondences between the patch. So like, let's say I'm gonna match like pixel in the patch, within the patch, I'm gonna match like -1, 1, 2 and 4, like 1 and -3 or whatever. And you can initialize that randomly. And then once you have that patch where the maximum gradient is always pointing in the same direction, then you want to take those sets of pixel correspondences and you want to say, okay, for the first correspondence, if the first pixel has a higher intensity than the second pixel, I'll make it a 1. Otherwise, I'll make it a 0. And then this way you create a binary string where each number in the string represents the intensity comparison between the two. And then that binary string becomes your feature vector for that, or becomes like a vector describing that feature, basically. So that's how we can uniquely identify the feature using that. And can someone tell me why it might be desirable to have the feature be a binary string? Just like, why might that be good for what the application that we're kind of doing? Like, why didn't we just make this vector like out of the intensity? Like we could have done something more complex and stored like the intensity stuff, but why might it be nice to have the binary string? Yeah. Yeah, it'd be much faster. So whenever we're working with binaries, especially when we're trying to do comparisons between features, I'll talk about this a little bit in a second, but it's extremely easy to store binary strings and extremely fast to compare binary strings. So this makes it, especially these algorithms are meant to run in real time, so this is an important thing that makes it able to run in real time. Yeah, I think we did. You guys talk about it. Like, how would you compare if I gave you two? Like, I gave you 0, 1, 0, 0, and 1, 0, 0, 1. Like, what's an intuitive way to compare these? Oh, yeah, XOR. Yeah. Okay. So for the initial setup of our algorithm, right? This goes back to the chicken and egg problem. Do we start with a localization or do we start with a mapping? And generally speaking, I think OrbSlam starts with mapping from using structure from motion. So structure from motion is basically like if I take a picture of everything facing this direction, and then I move slightly over here, and then I take a picture of everything in this direction, right? That gives me, in the picture, right? All the picture tells me is it gives me rays of where things are. But if I have two pictures from two different angles, then what I can do is intersect those rays, and I can get an estimate for where the 3D location of that is from two pictures. That's basically what structure from motion is trying to do here. So we're given two frames with a set of matching features. We assume that we already extracted the features and we've matched them up using the XOR of the binaries. And then we basically want to extract this essential matrix. So the essential matrix is like it tells you the relationship of the camera between two frames. And in order to find the essential matrix, basically the essential matrix has the property where if I take the features from frame 2 and I left multiply, and then on the right I right multiply with the same feature from frame 1, then that should be 0 for all the correspondences. And this matrix is a 3x3 matrix, but it's only defined up to a scale factor. So we have 9 elements in the matrix, defined up to a scale factor. So that means we actually have 8 degrees of freedom. So in order to solve this, we need 8 point correspondences. And basically, you can rearrange that top equation into the equation just like a matrix A times the essential matrix equals 0. And this is what A actually is. And then I don't know if you guys talked about singular value decomposition last time, but in a lot of computer vision stuff, once you get things in this solution, you just solve it by doing an SVD. It's kind of like it's
It's because like,
it's in the null. So basically, right? So the solutions that we're looking for E are in the null space of A, and SVD gives you a very easy way to find the null space of A. And if you don't know what that means, you guys should take a video on it. But so basically, null space of A is the set of vectors what A maps to that are not zero, but A maps them to zero. Yeah, that's what it does. And SVD just
and then
gives you
that's
that.
the best news that we're given, like, things are sliding off. So give me like an
Yeah, it'll still give you a very good approximation to make it as close to zero as possible. Okay. So once we have the essential matrix E, what we can do is the essential matrix E is generally like speaking of, you can get the essential matrix if you know the rotation and translation between two cameras. Right now, we can find the essential matrix from the point correspondences, and then we want to extract the rotation and translation from that matrix. So here we have this helper matrix W. It just looks like that. And you kind of use it. So once again, from E, once you have E, you do another SVD. That gives you U and V transpose. So the comma there is supposed to be, the apostrophe there is supposed to be a transpose. And then there are a couple options for R's and T's that'll satisfy E. So you can either do have R as U W V transpose or U W transpose V transpose. And then T is going to be either positive or negative. The third column of U normalized to a scale constant. All this is up to a scale constant. And then you can determine which pair of R and T is correct by using the chirality condition. Chirality condition is basically saying like, given that R and T, like if I actually had the R and T, would I be looking at the points? Like would the points be in front of my camera or would the points be behind my camera? That's all it's saying. So you have like, I think it's like 4 combinations of possible R's and T's, and then you just check this chirality condition for all the points that you were matching, make sure that they're actually in front of you as they should. And then once you have the R and T, basically like from this picture, right, you can extend rays from all of the pixels of the images, and then they're going to intersect some, like you see here. And then we can just, say that this is the world coordinate at this point, this is the world coordinate at this point. So this is our initial map. We use structure for motion in order to determine an initial map of these features in the very beginning. Okay, the next thing that we do is tracking. So now that we have the initial map, right? And then now we have an initial map. Let's say we move to another location. We extract features again, we do feature matching again. So now we have features that we can see in the world, and we want to know where our camera is again. And so the next thing that we'll do is use the PNP, perspective endpoint problem. So what the perspective endpoint problem, what the PNP problem is basically I have a bunch of 3D points, and I have the matching 2D points in my image, and I want to figure out how far away those 3D points are from the camera. There's a lot of different ways that you can do this. I just put one up here. This is, I forgot what his name is. I think it's Grunner or something like that. You can basically do trigonometry and solve this. If you do trigonometry to try and solve this, you'll get a 4th order equation, which we have closed form solutions for. So you can just solve for S1, S2, and S3. So then for S1, S2, and S3, if you can basically estimate the camera pose given that you know the 3D locations of the features because you feature matched and using the previous structure for motion, you know where those 3D points are. And then you know where the 2D coordinates are in your camera frame. So then you can tell how far away from each of those are, and then you can just triangulate yourself from those positions. So that gives you your camera RT. And now that basically gives us all the components that we kind of need for SLAM. So in the beginning, we get features and we use structure for motion to create the map. And then we move, we get the features from the new location, we localize our camera using PNP, we add new features that we saw in that frame that we didn't see in previous frames because we could use those to help localize ourselves in the future. We add those features to our 3D map, the 3D locations of those points, and then we move, and then we just keep doing that. And then lastly, there's this loop closing problem. So basically, if I notice that I'm in a location where I have been before, then I need to make sure that the R's and T's that my localization of myself actually like closes the loop. So I need to end up back where I am if I end up seeing the same picture that I did before. And the way that we do this is we do bundle adjustment. So basically, when you're running SLAM, you're just going to be comparing to like a frame some time ago. And if those frames are similar enough, like we see enough similar features between the two, then we'll be like, oh, okay, that means this is probably somewhere that we have been before. We need to make sure that we're kind of matched up. And bundle adjustment is just a minimization problem of this equation. So R here, RT are like the rotation and translations that we have been estimating for our camera pose along our journey. XJ, sorry, XJ should be like feature J within the two frames that we are matching that tells us that we're like in the same position. And then XIJ is the pixel is the location of the J of the I frame. Wait, sorry, is the location of the J feature in the I frame. So we're basically just like very simply put, what this equation is trying to do is we're just trying to minimize the difference between the actual location of each of the features in each of the frames compared to our estimation of the location of that feature and frame based off of the rotation and transformation matrices that we have. We're just trying to minimize that difference so that way it looks the same. Yeah.
You have a sequence of RNTs. You want to make sure that we're in the same place now, like if I start our original rotation and apply the RNTs like sequentially, we should get the same.
Yeah, basically. It's just trying to make sure that if we follow our localization map, if we follow the trajectory of our localization, then at the end the feature should be in the same place as what we're looking at now. That's all it's saying. And we want to minimize over that. And then there's a couple different algorithms we use. I think specifically for the Orb Slam version that I was looking at, they use 11-Berg Marquardt least squares optimization technique. This is just like there's like existing optimization techniques for that you can use for this. And just to give you an example of what OrbSlam kind of looks like, so you can see on the left here, this is the feature extraction that's done by OrbSlam. You can see that it's pretty good at picking out corners and things. And then here is a map of the estimated trajectory versus, you're going to ignore the optimized trajectory for here, and then versus the actual trajectory that we get. So you can see that's like pretty close. Actually, I think the optimized trajectory might be after they apply a bundle adjustment. So basically you can see here, you want to look at the difference between the green and the pink. I think the red is going to be like a real-time trajectory estimate that they give you. The pink is going to be an optimized post-processing trajectory, and then the green is going to be the actual trajectory that you see. And then that's what it gives you. And then the colors in the middle, those are all the features that it was detected. You can imagine like this guy was going around his desk, just like walking around his desk, and all those points in the middle are like the features that were extracted from the desk. Okay, cool. So that's like mostly what we'll do for SLAM. We'll probably look at more into actual algorithmic applications of that when we start working towards the IRX stuff, because that's going to be very important for that. For now, the next thing that we're going to be talking about is digit classification. So later today, you guys will be working on, I don't know if you guys remember last week, we gave you weights to do the image classification thing, right? And you guys are playing with filters and stuff. This week, you guys will be writing that classifier yourself. So given the MNIST data set, which is like the black and white numbers, you guys are going to write algorithms which can actually classify those. You guys should be able to get up to like 98. I'm pretty sure it's like 98% accuracy, like most basic CNN architecture. So that's what you guys should be aiming for. So really quickly, once again, just to go over the data set, we have 28 by 28 black and white images of handwritten numbers from 0 to 9. And this is what you'll be classifying on. You guys know what convolutions are. Ethan's talked about them. Convolutions, we use them to extract features. And you guys should know mathematically, it's pretty simple to apply. Pooling, you guys also talked about. Pooling is used in a lot of convolutional neural networks just to reduce data dimensionality. And there's a couple different types of pooling that are very often used. Max, min, average pooling. They're pretty self-explanatory for what they do. And nonlinearity. So I don't remember if you guys talked about specific nonlinearities. Okay. So, like mentioned earlier, nonlinearity is super important in convolutional neural networks because convolutions themselves are linear operators, which means that, like we were saying earlier, if you do a bunch of convolutions and whatever, you can make your network as complicated as possible with convolutions and fully connected layers and whatever. And at the end of the day, if you don't have any nonlinearity, I can make a perceptron with one layer that does the exact same thing that your thing is doing. So that's why we have to add these nonlinearity. So this is a very common one. This is called sigmoid. It just maps between 0 to 1 in this function. 10H, basically the same thing as sigmoid, except it goes from -1 to 1. And then here is one of the most popular ones that have been like in the recent rise of neural nets since like probably 2012-ish. So it's called ReLU. I don't know if you guys have heard of it, rectified linear unit. So it's called rectified linear unit because it's 0 here, and then it rectifies. So when it's negative, rectification brings it up to 0, and then here it's just linear. It's literally just y equals x. Yeah, remember the most like expensive part, generally speaking, of any machine learning is computing gradients and like backprop. Can somebody tell me what the gradient is here? Can somebody tell me what the gradient is here? It's very easy, right? So that's why people use it. It's very fast, very easy to use. And it also deals with a problem which I'll mention next, which is the vanishing gradient problem. So if I have some kind of like deep neural network and I'm multiplying by gradients all the time, you can see here, like let's say for sigma, right? What can somebody tell me like about what the gradient is over here? Close to 0 and like up here. Same thing for 10H, right? So once I get kind of towards the ends, it gets close to 0. And the problem is when I'm multiplying like a ton of gradients together, right? And one of them is close to 0, then like my gradient ultimately at the end is going to be like very close to 0, right?
Like even if it's like 0.9.
Yeah, even if it's 0.9. Yeah.
Yeah, we keep them multiplying them. They're gonna match zero. And sometimes you want this, right? We have okay, sometimes you don't want this delay.
Generally speaking, you don't. And like when the gradient vanishes, that basically means when you're updating your weights, because we update it relative to the gradient. So like we're basically gonna get to some point where nothing changes. Like our model does not actually get better. Yeah. So this is why ReLU is useful because here it's just 1. So it's just telling you that it's 1. It doesn't actually affect the gradient at all. So the gradient will just be dependent on the actual weight and like bias values. Yeah. Okay. Mhm. Yeah. Yeah, there's multiple issues to solve. There's multiple ways to solve this issue. ReLU is like one of the simplest ones that people have come up with. And it's like very easy to just like slot into your neural network. Something else that helps, generally speaking, with neural nets is dropout. So this may seem counterintuitive, but basically what dropout does is you assign a probability, and then each time you're updating like weights, you just like with the probability p that you assign, you just kind of like ignore this one. You just don't update this one. And like same thing for all of them. You just with some probability, you just don't update it. Can anyone explain maybe why that might be a good thing? It is less computationally expensive, that's true. But so one of the big things about dropout is it actually improves the generalizing capability of functions. I don't know if anyone can maybe take a guess at why that might be. Yeah. Overfitting, good. Yeah, cool. Yeah. So dropout's very useful. People have seen like a lot of improvement just like applying dropout to their existing networks. And then towards the end of most convolutional neural networks, you'll have fully connected layers. This is just a perceptron. You just flatten the data, you pass it through here. And then at the very end, if you're doing classification like you guys are going to want dimensionality. Let me ask you, what should the final columns dimensionality be for the MNIST data set? What are you guys trying to classify? Digits. Yeah, what did you say? Okay. Yeah, 10, exactly. I mean, we have 10 digits, so we want our final layer to be 10 things. That tells us kind of whichever one has the highest number is usually what we go with. Yeah, what's up? Okay, yeah, perceptron is basically just one of these. Yeah, perceptron, you can just think about it as like it's a neural network where all of them, we're generally speaking, you just have these linear like layers, and then they're linear connected, usually fully connected between all of these, and it's just basically just doing that. Yeah. 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 Cool. And then so how do we actually choose CNN architecture? I haven't done a bunch of recent literature on this. I was more looking at this kind of like 2 years ago. But I think generally speaking, a lot of times for literature, for architecture, a lot of research is currently ongoing for how to do architecture. But generally speaking, there's a couple like well-known architectures that have historically been good at problems and have been historically good at solving other problems that were not what they were originally built for. If you're interested in doing architecture, this is definitely a big area of research, I'm pretty sure. So like you guys can look more into it. But I'll tell you guys a little bit about the history of kind of the most popular architectures that people have done. So Linnet was first built by Yann LeCun. I don't know if you guys, I don't actually know how to pronounce his name. Is that how you pronounce his name?
No, I just sound like.
Oh yeah, yeah. It does, it does. So I mean, you guys, I don't know if you guys have heard of him. He's pretty popular. He's pretty famous in the.
He's the first one like trained like class for digits. He created it.
Yeah, he created them. So this is the OG kind of convolutional neural net. This is what I think you guys should try to aim for today as a baseline. Like even with the very OG one, like you should be able to get like that 98%, 99% on the data set. Then we have AlexNet, which was made in 2012. This was for like it was like one of Google's image classification competitions, I think. And it beat out a bunch of the other more traditional models. There was a time where neural nets, it was like at the dark ages of neural networks, like people didn't really think that they were useful, which is kind of stupid when you look back on it. But so AlexNet kind of started this resurgence of interest in neural networks because it was able to win that Google competition. Then we have VGGNet, which is like, it was a very simple, I think it might have like 1 or 2 convolutional layers and like maybe like 3 fully connected layers. It's like a very small convolutional layer now, but it still works very well. Then we have GoogleNet, which is where you kind of have parallel convolutions going on. So not all the data is passed linearly. You have some data going this way, some data going this way, some data going, and you do that in parallel, and then you combine them at the end. We have ResNet, which has some better methods against vanishing gradients. I think what they do is they do like, yeah, they do skipping. So basically, like if I have the layer here, like layer 1, layer 2, layer 3, layer 4, like some of the data from here will skip like over here. And then when you're calculating the gradient, basically because this data was influenced by this data, this gradient, you don't need to calculate all these intermediate gradients. You can just go straight from here to here. So eliminate some of the vanishing gradient problems because we just do less gradient multiplication. And then we also have MobileNet. I think this was developed by Google. And I think it's much less computationally demanding. I think that one can run in very easily on like your, like it can be like trained on like your phone or something like that. Yeah. So you guys are going to be working with, I think I would recommend just going with Linnet and then doing optimizations afterwards. Well, it doesn't really matter. That's true. Well, I mean, Linnet, like these aren't that hard. I have some stuff on PyTorch in here, and you'll see like it's not really that hard to actually implement in PyTorch. Like Ethan was saying, like PyTorch makes it extremely easy, especially the gradient part, which is like the hardest part. Like it's literally just like one line of code, and it just does everything for you. Yeah. So for the Linnet architecture, just like we can just walk through this really quickly. Like say you have an image. This is just like the default architecture. I would recommend starting just so you can follow it. It's not that hard to do. So you're given MNIST data, which is 28 by 28. You can just scale that up to 32 by 32. I think there's a way that you can just like transform the dimension. I think it just pads it with 0, so it'll just like add black to the outside to make it 32 by 32. It's very easy to do. Then after that, you do 6 convolutional layers with a kernel size of 5 and a stride of 1. You guys remember all what kernel size and stride mean? Oh, okay. Okay. Well, then let's go. Yeah. Okay. So like I have a like I'm just gonna do like random numbers. So like let's say I have a kernel of 2, right? So my kernel size is gonna be this. I'm gonna apply my convolution operation to this number. So my kernel size is just gonna be like the dimension of this. Um, and then my stride is basically how much I move in the image. So like if I have a stride of 1, then the next set of data that I'll consider is just like this box. And then if I had a stride of, let's say, 2, I would instead consider this box. Like basically I would move 2 to the right instead of 1 to the right. It's very easy. It's just like how much you move to the right. Then there's also something called padding. I don't believe Lynette uses any padding, but padding is something that's often done if you just want to like play with the dimensionality. So like, let's say I want to do this convolution, but I don't actually want to decrease the dimensionality of my data at all. So let me just redraw this and then I'll ask you guys a question. So let's say I have a kernel size of 2 and I want the final output of my data to not have any data dimensionality reduced. Padding is basically where I just go around the outside and I add some number of layers of just like zeros on the outside. So if I wanted a kernel size of 2 with a stride of 1 and I didn't want to reduce the dimensionality of my data, how much do you guys think I should pad by? Like I want my final output after the convolution to have the same 4x4. 4x4 size. So how much do you guys think I should pad? Yeah. Yeah, exactly. So if I just add 1 layer of zeros, right, then I'll have like this all the way, and I can move this way 4 times, right? So that'll give me 4, and then this way 4 times. So like 1, 2, 3, 4. So that'll give me a 4x4 after I'm done with my convolutions. Yeah. Okay. So most of the dimension stuff you can like just kind of reason about in your head, and it shouldn't be that hard to think of the dimensionalities that would actually fit. So after we have, so the first one we do 6 convolutions of 5x1s. Then we have, I think that is a max pool or an average pool, followed by more convolutions, followed by more pools, and in between we're obviously adding nonlinearity. That's super important. I think in the original one they used sigmoid. I think this was before people really introduced ReLU. Don't use sigmoid. I would use ReLU. And then at the very end, so after you get to here, you basically just like flatten all of this. So flatten it in terms meaning like at this point when you do convolutions, right? If you do a convolution on a 2-dimensional image, you're gonna get a 2-dimensional product, 2-dimensional result. For the fully connected layer, we want just like 1-dimensional tensors. So you just want to flatten it into 1-dimensional tensors and then pass it through 3 fully connected layers with those sizes specified, and then you want to end up with a 10 size output. Yeah. 1-dimensional, so it's just like an image is 2D. I'm not even gonna write this out. An image is 2D. When we do fully connected layers, the inputs are just like a column. So it's a 1-dimensional vector. Like when I say 1-dimensional vector, it's just like it's just a 1 column vector as opposed to some length and some width. Yeah, okay, cool. So why don't we get started on that classification? If you guys can go into your VS Codes, whatever IDEs you're using, and then first download PyTorch if you have not done that before. Okay. Oh shoot. Oh, and one more thing about PyTorch, I'll just let you guys know is PyTorch also has the like a very easy integrated ability to work with CUDA. Do you guys know what CUDA is? Okay, cool. So CUDA is you guys know what NVIDIA GPUs are, I'm assuming. So CUDA is basically a programming language that you can use on NVIDIA GPUs. And instead of using the CPU for like arithmetic calculations and stuff like that, you just use the GPU, which is like orders like many orders of magnitude faster than using your CPU. And using PyTorch, if you have a GPU mounted, it's very easy for you to actually find the device that's like CUDA compatible. So CUDA compatible meaning is it's just like it's an NVIDIA GPU. And then it'll do